We can see it.
Okay, so you can see my screen?
Yep. Yeah,
okay.
It looks good.
So yeah, I definitely can't see anyone, so it's completely fine to have your camera off. So thanks for inviting me to give a seminar. This is my first invited seminar, so we'll see how that goes. And today I'm going to talk about a framework for convergent global optimization and regression that I've developed in constructive type theory. So I sort of presumed that this would be quite different, but based on what was said in the former, like it seems like a lot of people are interested in this sort of stuff anyway, which is quite cool. So this framework's fully formalized in the Agda programming language, and it operates on a general class of types that includes representations of exact real numbers. So this might be a little different to what you're used to. It's at quite a high level of abstraction, as is a lot of things kind of when it's formalized. And the framework's sort of its own like foundational theory that's been built from the ground up to try and characterize certain things about this theory of optimization and regression. So feel free to just sort of take everything with a pinch of salt, enjoy the ride of the talk and everything. So first I'll just introduce talking a little bit about optimization algorithms. So core component of machine learning, broad applications to function approximation algorithms like interpolation and regression. And you know, in recent years, local optimization algorithms such as gradient descent have received a tremendous amount of focus, and rightly so. You know, in the 90s, the emergent availability of data-driven approaches to machine learning successfully forward the AI winter of the previous 2 decades. And these approaches utilize local methods as a backbone. But in a kind of very naive sense, the theoretical guarantees given by such methods are not always ideal. We have to tune the algorithm very specifically, rerun the algorithm, but we always have the chance that we can discard the best solution. Meanwhile, global optimization algorithms are nowhere near as practically available or efficient, but they never discard the best solution. That's kind of their modus operandi. So in this sort of branch and bound style approach instead, the function space is repeatedly split and the candidate intervals are bounded using continuity information about the function in order to progressively zoom in on the global minimum. And we can discard certain candidate intervals when we find like strictly better ones. And eventually we're going to zoom in on this sort of in the infinite. But this in the infinite, you know, that already gives a sense of how this convergence process is inefficient. So these sort of algorithms were the starting point for me of thinking about this sort of work, not being from a background of AI or machine learning, but bringing it down to this foundational level. And we wanted to kind of ask, in a type theoretical sense, can we develop convergent algorithms for global optimization within type theory on a general class of types? And what would those types look like? And can we get interesting properties? Can we develop interesting types for that general class of types, like specific instances? So, and then furthermore, we draw connections between these sort of initial results and a generalized notion of parametric regression algorithms, which was sort of keen interest to us at the start. And like I say, we have to ensure that these verified algorithms are at least somewhat useful to us. They may be very inefficient, but they have to relate in some way to what people would like to do with optimization or regression or machine learning. And so we build our framework with the sort of specific intent of application to data types for exact real numbers. So if you did watch Bob's talk last week, which we talked about earlier, that will be a little bit of an introduction, I suppose, to some of the things that we do later in this talk. And for the interested type theorist, we contribute to the area of sort of analysis and type theory in a couple of small technical ways that I'll detail later in the talk. And as I said, it's all formalized in Agda. And not in a complementary way, but like as a key part of the research program, which increasingly like people are doing, like they're doing the work in Agda. They're not just formalizing the work they did on paper in Agda. And so first I want to talk about data types for real numbers. So a type theorist is basically just a software engineer who found a whiteboard marker. Like, so when we say real numbers, we're very interested in what specific computational representation are we talking about. And obviously floating points are usually utilized representation. And I would label these as a discrete data type for reals. What I mean by this is that they have a very high level of precision, of the real line, but this granularity of a real line is fixed. We can't subdivide it forever. We get to a point where 0.1 doesn't equal 0.1, and we can't get any closer to 0.1. And that's I'm not saying like I've discovered something new here. This is obvious. To get these efficient algorithms, this is the sort of payoff here. But if we think back to our branch and bound approach, which I showed earlier, we won't really be able to give a sufficient definition of a reliably continuous function here. And that means that we can't really develop interesting convergence theorems for optimization using floating point numbers. Because we'll get to a point essentially where we'll say, well, this is as good as it gets. The continuity information isn't going to tell you anything more. These squares are not going to get any smaller now for branch and bound approach. And so at that point, you've just got to pick the best one. And maybe that's fine, but we want to look at a more general type system and see, well, what else can we do that's more interesting than that? So our framework is instead developed for what we would like to refer to as continuous data types for arbitrary granularity real numbers. They give us kind of dynamic granularity of a real line, which we can kind of keep subdividing areas or look at certain areas, zoom in, zoom out. We can do this sort of stuff. So what do we mean by constructive reals? And this may be new to some of you, or it may be very old to some of you. But there's loads of different ways to explain what constructive reals are. So for example, the informal way I just described, a data type for constructive reals is one in which the granularity of a real line is dynamic. So if you think you can give it a precision level, and that will give you a smaller and smaller interval of the real line. And if you imagine if you could give it an infinite level of precision, it would give you a single point. So it converges to a real line itself. So constructive reals, another way of describing them, are those real numbers that can be constructively located. So given any two rational numbers, we can locate the real either above one of them or below the other. They're also real numbers that can be, in a more computational sense, that can be reconstructed by an algorithm to any degree of precision. So if we think of a kind of Turing machine, like this is a very naive Turing machine-like representation, but we can kind of look at pi and we say, well, give it us to say 3 decimal places, that's 3 layers of precision, say, and then, oh, give it us to 4 layers of precision, give it us to 5, give it us to 6. And as I say, this infinite process eventually in quotes, because it's an infinite process, converges to a real line, because we'll get the actual number. But I'm interested in one particular representation, or one particular class of representations in this paper. And that's the family of types for signed digit encodings. And signed digit encodings allow numbers in compact intervals to be represented as infinitary sequences of discrete types. And I'll explain that a little bit more in a bit. So for example, so this is kind of a general view of that. So a compact interval minus n to n is represented as infinitary sequences of this type, from the naturals to a certain number of integers, and then you say, well, the real number represented is this infinite sum. But to give a more specific example, and the one we use in the paper, is just the interval minus 1 to 1. And these are by streams of type. So the function is from the natural numbers to minus 1, 0, or 1. And we call this type 3 to the n for obvious reasons. And then, so an encoding of type, say alpha of type 3 to the n, represents, you look at the first digit, divide that by 2, then add the second digit, divided by 4, then add the third digit, divided by 8, and you keep doing this. And that gives you this convergence property that I said. So this dynamic granularity, what we meant by that is that, well, if we look at a real line here, we have representations of minus 1, which an infinite number of minus 1s, 1, an infinite number of 1s, and 0, which can be represented in many different ways. And observing each successive digit of a stream allows us to locate the represented number in an interval half the width of that which we had previously. So what I mean by this is, like, if we look at 4 digits, then we locate the number in this interval of width 2 to the minus 4, 1 over 16. And if we add one more digit, then we get a half the interval. We're now at 1 over 32. And we keep doing this. And this is exactly what we meant by dynamic granularity. We can ask for more and more precision as we require it. And obviously, if you imagine if you had an infinite number of digits, then that would give you the exact number, of course. So now I'm going to attempt to move over to our Agda framework to kind of explain a few concepts just straight from the horse's mouth, as it were. As I say, all the work is done in this framework, and it's public. You can go and look at it if you want to put yourself through that pain. So we've got many different files here, and in the README file, I kind of connect it to this paper that we've got at LIX. And sort of every definition or theorem we have is connected to something in this library. And that's kind of the way that I want to do mathematics, the way I want to do maths is, oh, you've read this definition in the paper, here's the proof. So if we go into this file for signed digits, we find our type of signed digit encodings that I told you about, 3 to the n. So they're an infinitary sequence of a discrete type, as I said. So the discrete type is up here, 3. We have -1, 0, 1. And what we mean by a discrete type, we have a proof of that here, is it's just if you have 2 elements, you can decide whether they're equal or not equal. So these are equal, these are equal, these are equal, these are all not equal. And that's important for something that we'll look at in a short while. And then we have loads of operations defined in Agda. And this is all based, by the way, on Martin Niscardo's work in a Haskell library that he developed a few years ago on the same type of encodings. So I've worked with Martin, he's my second supervisor, and we've kind of built this. I've built this from his work, and then I've gone a bit further and improved a few extra things and a few things that I've obviously not brought over to this framework because it's not useful. So how do we do different operations? Well, let's look at negation. So we define a complement function for 3, and then the negation function is just a map of the complement function. That's very easy. Addition, sorry, not addition, the midpoint, because we can't do addition, obviously we're in a compact interval, is a bit more difficult. So we come up with another intermediate representation, which gives us bigger intervals, -2 to 2. And then we add our digits, our 2 digits in 3, and then we have a function where we have 2 streams in -1 to 1, or the representation of -1 to 1, I should say. And we take it to the representation of -2 to 2. And then we have a function which is defined in a bit of a crazy way, but divides a number in the -2 to 2 representation back into -1 to 1. So we kind of go, we take these 2 streams, we go up, and then we divide by 2 and go down. So that's how the midpoint is defined. And you may be looking at this and just say, well, I could just change any of these digits and this would stay the same. How is this going to be provably the midpoint? And we'll come to that a little bit later. And then we also define multiplication, which then it gets a bit crazy because we have to use a really big intermediary representation, and that just takes ages to define. But we do get to a point where we can define multiplication, and we can also define the infinitary midpoint, which is quite surprising at first that you can define that, but that's actually a continuous function as well. So as I said earlier, that we want to these continuous types of real numbers will be able to give us a reliable definition of a continuous function. But I also said that our framework would be defined on a general class of types. And so what we have to do is come up with some sort of general notion of continuity in our framework. So let's try and do that. So continuity would usually be defined using metric spaces. And they have the real numbers, obviously, as their like measurement type. But we don't have a computable definition for real numbers here at the moment. And we don't really want to have to like build the real numbers in just so that we can do like this continuous functions on representations for real numbers. That feels a bit like cyclical almost. And so what we opt to do instead is utilize cometric spaces with the co-natural numbers as their measurement type. So this is the library type topology, which is what my library is built upon, and it's by Martin Niscardo as well. So I'm not using the standard library. If there's any Agda standard library converts here, then I'm sorry, I'm not using that. I'm using type topology instead. And this library has loads of things already proved in, a few contributions by myself for this paper as well. And so what we take from this here, I did consider sort of putting slices into a PowerPoint, but I thought it would be more interesting to actually just see how the whole file fits together. Also save me a bit of time. So if we look at the co-naturals here, these are the natural numbers, of course, with a point at infinity. And the way we represent them here is as an infinite binary sequence that is decreasing. So we mean that the next element is either the same or smaller than the last element. That's defined here. So for example, 0 is given by an infinite number of zeros. 5 is given by 5 ones and then an infinite number of zeros, and infinite is just an infinite number of ones. So you can see there how you get a representation of the extended naturals. And this is what we're going to use as our measurement type for cometrics. So how do we define our cometrics? Well, we begin by defining what we call a codistance function. So rather than a distance function, it's like a closeness function. So if we consider a type x, then the codistance function is going to say, well, if cxy is infinite, then x equals y. So rather than dxy is 0, then x equals y, we're saying how close things are. If they're infinitely close, then they're equal. So the idea then is that, so we have this with the infinite point, but if we have this, so we have cxy equals, under just means we're lifting of n to a extended natural. So if cxy equals n, if the codistance between x and y is n, then the intuition here is that x and y can be distinguished by a finite amount of information of size n in some way. So what I do first here is define a cometric on our class of types that are infinitary sequences of discrete types, also known as the class of types we use for signed digit encodings, including 3 to the n. So we open up this module here with some sort of type D, a discrete type. We have the proof that it's discrete, and then we have the S here, the sequence is the infinitary sequence of that D type. And to define the codistance down here, what we use actually is the co-recursion property of the co-natural numbers. So briefly, I can show you the co-recursion property. I'm not going to go over this in a huge amount of detail, but the idea here is that the codistance will be this recovered homomorphism H. So for every type X, and X here is actually 2 streams of discrete type, because remember, we're comparing 2 streams for the codistance of them. So that's the X here, 2 streams. So just keep that in mind. And then the kappa here is a function that we have where we say, well, given 2 streams, well, we have 2 functions. Given 2 streams, if the head of one stream is equal to the head of the second stream, then we get something of type 1 plus 2 streams. So if they're equal, we just give back the tail of the 2 streams. And if they're not equal, we give back the point 1. And so this is a bit confusing here, but the idea is that using this P, we take 2 streams, we compare the first element, and using this delta, which is the proof of decidable equality, remember. So we compare the head of the sequences, and then if the 2 sequences are equal, we give back the tail of the 2 sequences. If they're not equal, we give back just 1. And you can kind of think of this as like a ticking clock. So if you look at the head of the 2 streams and they're equal, then the clock keeps ticking. You go to the next bit, you go to the next tick, you go to the next tick, until you get to a point where they're not equal, and then you return 1, and that's like the clock stopping. That's kind of the intuition here. And what we do is we use the co-recursion property on that function to define the codistance. So if we look down here, remember that our kappa is the comparison operation on this ticking clock sort of system. If the clock stops, then we give back an infinite number of zeros, or 0. And if the clock keeps ticking, then we perform the operation again on the tail of the sequences, and we get a successor. And what does this all mean, like away from the co-recursion? What does it sort of analytically mean? Well, it means these 2 things. So if you have 2 streams and the head is not equal, then the codistance is 0, because the finite amount of information you needed was at point 0. And now if the head is equal, then the codistance is the successor of the codistance of the tails. And so you can see here how if you have 2 streams that are equal, you're going to have the successor of the successor of the successor of the successor. The clock's just going to keep ticking forever, and you're going to get, essentially, you're going to get the infinity representation. And we then derive some properties from this. So for example, that property I just said about that given the same sequence, we get infinity. And also that if the codistance is infinity, then they're equal. This is all proved here from co-recursion properties. Also, the codistance should be symmetric. That makes sense. So codistance between A and B is the same as the codistance between B and A. And finally, we get what we call the ultrametric property, which is a very long proof. But basically what it says is it's kind of like a version of the triangle inequality. So if we have A, B, and E, then the minimum codistance, so the minimum of the codistance between A and B, or the codistance between B and E, is always smaller than the codistance between A and E, or equal to. That's kind of like the version of the triangle inequality. So all these things are proved. And so what we have in the end, we derive many codistances from it. So these four properties that we had, that I just showed you, if we have these four, then we call this a codistance. And then we prove that any type, any infinitary sequence type of discrete elements has a codistance. So 3 to the n has codistance. I don't know, n to the n has codistance. 2 to the n has codistance. And also the extended naturals themselves have a codistance. So we get all these codistances, and chiefly the one we're interested in is 3 to the n for our signed digit encodings. So I said we wanted a general class of types for a general sort of continuity definition. And so we have to be able to do more codistances than just that. So the one that I don't have in this file, which is the most obvious one, is the discrete codistance, right? If you have a discrete type, you compare the two elements. If they're equal, you return infinity. If they're not equal, you return 0. That's all you need to do. So that's the sort of basic codistance. And then you can do a product codistance. So if you have two types that both have codistances, then you can define the codistance on the product of those types by just saying, well, compare the first element and the second element, take the minimum, and that satisfies all the properties. And then that will also give you not just binary products, but if you have one codistance type, you can have any finite product. So what we now have is like discrete types, and then products, finite products, and then also in a sort of sense we have infinite products of discrete types because we have the sequences I talked about. And then we get to our definition of continuity. So now that we've got this general class of types that we can do lots of different things with, lots of different types satisfy it, we need a definition of continuity that works for all these types. And so what we do is we essentially just define the epsilon delta definition of continuity, but on ultra cometric spaces rather than on metric spaces. And so what we say is, say we have two types, x and y. They both have codistances, and there's a function from x to y. Then this function is continuous if for all epsilon, and then we have to look up here, there is a delta such that for any x and y, if the codistance between x and y is above delta or equal to, then the codistance between fx and fy is above the epsilon. So this is the classic for all epsilon, there is a delta. That's all it is. And what it does is we say, well, we want to be able to distinguish the function to this point. How many points do I need to distinguish the arguments to? That's all we're saying here. And this, because we've got a general class of types here, we could define this on, this works for any type that we just said. And then we also get a definition of continuity on predicates as well. Predicates in Agda, you could do them as functions from x to the 2, or you can do them just as like from x to a universe of types. And that's what we do here. So if a predicate is defined as x to the universe of types, basically what it means is any type is a truth value, and if you give back the empty type, that's a false value essentially. And we can also define predicates to be continuous. What we mean by that is you just say that there exists some delta such that for any two elements, if the codistance is at least delta, then if px is satisfied, then py is satisfied. So what we essentially have here is for functions and for predicates, we have a constructive like delta for any epsilon for functions. You obviously don't need that for predicates, that tells you how far do I have to look in the arguments to either know that the two functions give the same up to epsilon, or for predicates, know that they give the same answer. So for a predicate, then basically what you have to say is, I have to look this far to know that the predicate is either satisfied or not satisfied. And that's what we mean when we say a continuous predicate. And then there's some other properties. So you'll notice the key item on Q that I never require that the stuff here is a codistance by the 4 things that we said earlier. And that's because you can still get a type for continuity from just functions, but it won't really be a type for continuity unless you've proved these 4 things. So we don't need to front load all of this into these definitions. But there are certain properties that we do expect our codistance functions to satisfy when we use them for analytical purposes. So for example, if we have a codistance function on y, we would expect that for any x, the codistance is always above any epsilon. That's the exact same as what I said about the cy xx would be infinity, but this is like a more analytical way of saying, well, it's just always above any epsilon. And then we also have another property, which we call right continuous. You could also have left continuous, but we just picked one, where you say you have the codistance function, and then for any epsilon, given an x and y and a z, if the codistance between x and y is at least epsilon, then the codistance between z and x is approximately equal to the codistance between z and y up to point epsilon. So what this means basically is if you have 2 elements that are indistinguishable up to a certain point, then if you compare those elements with a 3rd element, then the codistance you get from those 2 processes is also indistinguishable up to the same point. And this is a property that holds for like the codistance functions that we use, but we need to prove that because this is really significant, some of the proofs that we use later. And there's loads of other stuff here to do with. This is proving that all this stuff satisfies. So for example, the codistance on discrete sequences is right continuous. We have lots of different proofs here about all this stuff. And none of these proofs use any function extensionality or any univalence principles. This is all just in bog standard constructive type theory. So recap, what have we got so far here? We've got our codistance types and we've got continuity on codistance types. Now what we look at are these things called searchable types. And searchable types are basically the backbone of, if we think right back to the start of the talk when I introduced this stuff, of our constructive framework, our general class of types. So what are searchable types? Well, a searchable type is a type X that given any predicate that is, I call them detachable, they could also be called decidable predicates. Basically all we mean is that a predicate that given any element of X, we can say whether it's true or false. So you couldn't have, like if you had like a signed digit, for example, you couldn't have the predicate, all of these elements are 0 because like you wouldn't be able to answer that for any stream because you'd have to look at an infinite number of elements. So it has to be decidable in some way. And that's obviously linked to it being continuous, but it's just decidable is kind of like a relaxed version of continuous. You say, well, we know we can decide it in some way. So given any predicate, any decidable predicate, we can exhibit an element such that if at least one element satisfies the predicate, then that element does. And what does this mean? What it means is essentially we're constructing like a search routine here. So we have a type X, we give it a predicate, and we get back some answer. And if that predicate is satisfied by at least one thing, then it's satisfied by the thing that we got the answer from. So we're basically searching a predicate. We might get back garbage, but if we get back garbage, but we'll only get back garbage if nothing fits that predicate. If at least one thing does, then we'll get something that suits the predicate. And that's how this search algorithm works. Now, what types are searchable? Well, obviously every finite type is searchable because you just check every element just for one that suits the predicate. And if none of them do, then you just return the last element that you find. Basically, you just return. You search the first 10 natural numbers, and if nothing suits it, you give back 0. So that's fine. So 3 is searchable, what we talked about earlier. N is not searchable, obviously, because that would be like the limited principle of omniscience, because we're then saying, does 2 satisfy the predicate? Does 3? Does 4? Does 5? Does 6? And Obviously, if we get to a point that does, we can return it. But if we never do, then this is just completely uncomputable. But what might surprise you, might not, is that some infinite types are searchable. And this was proved as kind of non-constructively by Martin Esgardo 10 years ago, where basically he calls these compact types instead of searchable types, but they're the same thing. And what he proves here is that if you have a sequence of types that are all compact, then the sequence of those types is also compact. And a corollary of this would be that all our discrete sequence types are searchable. But we've got the Agda flag terminating here. This means that this file is unsafe. We can't actually compute anything from this proof. It's a really good proof, but unfortunately we can't compute anything from it. And that's because what Martin's essentially doing here, although it's not quite clear, is that all the predicates he looks at, although they're all decidable, like I said, we don't know how far we have to look. We don't know how much amount of finite information we have to look at. And that's really important when we're dealing with infinite types. So we don't have proof that these predicates are continuous. But as you've already seen, I've put in my framework a definition of what a continuous predicate is. And so what we're able to do is build on that and give a sort of subset of searchable types, a superset of searchable types, which we call continuously searchable. And we just add one extra condition, that the predicate we want to search is also provably continuous, meaning that not only can it be answered given any element, but we explicitly know, because this is uniform continuity, we explicitly know how much information we have to look at to get an answer. And that is obviously important for our signed digits. So basically you give it a predicate, like maybe like the first 100 elements are 0 or something like that. And the continuity here says, well, you only need to look at 100 elements, right? And therefore what you've done is you've got this infinite type, but you finitized it. You only have to look at the first 100 elements. And then it's sort of like, on paper, this is just like, well, this is obvious. You can just search it as a finite type now. But in Agda, in a formal way, proving this takes a bit of experience. I wanted to go over the proof for this a bit more, but I'm not sure I'll have too much time. But essentially, this is the proof here that if we have a discrete type that is searchable, then that the infinitary sequence on that type, using the codistance, because remember, this type is continuous, and so we need a codistance on that type, which the searchable type obviously didn't need a codistance, but continuously searchable does. So given, I'll start again, given a discrete type that is searchable, then if we have a codistance on that type, which we do because we defined it in that module earlier using the co-recursion principle, that is continuously searchable. And this is a proof just by induction on the modulus of continuity on the predicate. So if the modulus of continuity is 0, then that's easy. It follows vacuously because we don't have to check any information to know that just exhibiting any element is a satisfactory answer. Otherwise, we construct basically 2 predicates, one of which is on the head of a sequence, which we then use the searcher for the discrete type to look at, and one of which is on the tail of a sequence, but will have a one lower modulus of continuity. And so this is just an inductive argument here. And this is kind of like a corollary of what Martin proved. It's not quite as extravagant because I'm just proving that all discrete sequences are continuously searchable. But now this is computable. There's no magic here. There's no function extensionality. There's no non-termination. This just works, and we can use it in our algorithms. We also prove that product types, so searchable types, we have finite types, products, and coproducts. Obviously, continuously searchable types, if you have 2 types that are continuously searchable, then the product of those types is also continuously searchable. And then finite products of those types are continuously searchable. That's neat as well. And I haven't proved this, but it should be the case that the kind of proof that Martin had is also completely works in terms of continuously searchable. So if you have an infinite stream of continuously searchable types, then that whole stream is continuously searchable. But that's getting a bit abstract and not really what we're looking at. So what we've now got is a definition of continuity. The continuity works on our type 4 constructive real numbers that we've got, the -1 to 1 space, or any signed digit space as it happens. But I haven't answered the question that I asked earlier, which is, well, what if I just define all the operations on signed digits incorrectly? Then I'm not really searching the real number. So I know I can search these representations, but am I really searching the things I'm trying to represent? That's not convincing at the moment. And so what I've also done in this framework is I formalized last year this specification of the same interval -1 to 1. So we've got a representation in 3 to the n. We've also got a specification, like an axiomatization. So obviously this isn't there's no computable content here. This uses extensionality and stuff like that. But what we get here is like an axiomatization of, so if I'll scroll down a bit because this is very heavy. But what we essentially get here is we have a specification of the endpoints of the interval. We have the midpoint operation, just like we had on the representations. We have a negation operation. We have a multiplication operation somewhere here. And so we have all the sort of specification for all these things. So for example, we know that multiplication should be commutative. And this is a very, I could have just used all the field axioms and proved stuff. But this specification is sort of specifically built for this compact interval. And you get very, like, look, I only have a few hundred lines of code here, but you get a very nice representation of these basic axioms that you want for an interval. And this is based on Martin Escardo's interval object, Martin Escardo and Alex Simpson. And we also get associativity of multiplication. So we get all these proofs of the specification. We've got all this stuff on the representation. And then what we do is we connect these two things. And this is new to this paper. So we connect the signed digit representation to the interval object specification. And, these points, so for example, -1, 0, and 1 are obviously represented by the endpoints of the interval. And then what we prove are things like the negation operation on codes realizes the negation operation on the specification. And we do the same for midpoint, and we do the same for multiplication, and we do the same for the infinitary midpoint. And these are heavy proofs, but what we get here is sort of it's like a massive sanity check, essentially. Like, what we now know is that when we're searching these representations, we're not just sort of arbitrarily pushing around digits. We're actually searching a type that we reliably know represents the interval that it's supposed to. So if we search a function, if we search a predicate based on the multiplication function or a polynomial using the midpoint, obviously a medial polynomial, we know that we're actually looking at representations of -1 to 1 on a function that also actually represents a polynomial on -1 to 1. So as I say, it's like a huge sanity check. I'm going to go back to the slides now for the last bit of a talk, which is the theorems that we've proved. So I've brought all this stuff about general class of types, codistance, signed digits, continuity, searchable. All this stuff's a bit hazy at the moment. How does it all fit together? Let's have a look. So, how does it go back to what we were talking about earlier about optimization and regression? We've got quite far away from that, it seems. And so our general framework for regression begins with a generalized view of global optimization using the conaturals, as I said. So we have a definition of what it means for one conatural to be less than or equal to another conatural up to a certain degree of precision. So this is a bit of a weird one, really, but obviously we can't prove that we can't have a definition for less than equal in total that we can search. We need a finite amount of information. So for example, 5 is obviously less than 8 to any degree of precision, but 8 is less than 5 if we look at a small number of degree precisions, because it will only compare a finite prefix of these sequences. And then we get an optimization theorem from this, which we're not super happy with, to be honest. what we say is for any searchable co-ultrametric type, so these are the types I introduced when we looked at Agda, and any uniformly continuous measurement function, so the type is x, the measurement function is x to the extended naturals, and any precision level, then we can construct x0, which satisfies for any x, x0 is the optimum argument. So it's better than x. It's got a higher codistance. It's a smaller essentially measurement because it's codistance. Remember, up to point n, and this is kind of like a basic convergence theorem. We can increase n, and we get a better and better argument. And of course, the argument could jump about because up to point say 10, the best argument could be here. Up to 12, it could be here. It could completely jump about. But the idea is that in the infinite, this will converge in some way. It's not quite convergence of like, oh, you end up around this point and then smaller and smaller around this point. It could jump around a lot. But we get a sort of theorem about optimization on these types. We're not super happy with it. So let's see what else we can do. Well, we can apply this kind of theorem to regression. We want to extend this framework towards regression. And in any function approximation process, we want to compute some reconstructed function from some data observations. This is like bread and butter machine learning, essentially. And in our view, in our perspective, our constructive type theoretic perspective, we see these observations as coming from some data oracle, which we'll call omega. So that may or may not be subject to observation errors. So we have all these observations, but they must come from some sort of function. There must be some real relationship that we're estimating here. And the goal in function approximation is we have some loss function, which we're going to use the extended naturals as our measurement type. So we compare two functions. And what we're trying to do is minimize the loss, although in our case, it's actually maximizing the closeness between the reconstructed function and this unknown oracle. That's essentially what you're trying to do, which may just be a reconstruction from these data observations, of course, like a least squares sort of observation. So, and then we say a function approximation process, any function approximation process, we say is convergent if you can minimize the loss to any degree of precision between the original oracle and the reconstructed function. And there's two key families of approximation processes, interpolation and regression. Convergence properties of interpolation very well studied, and what we wanted to look at more were convergent properties for regression. And so in regression, you depend on the choice of some appropriate model function in parametric regression, right? So you're trying to reconstruct some x to the y, but you're dependent on a choice of parameters of type P, we'll say. And you could choose a completely inappropriate model function for what you're trying to do. So a model function is appropriate if it matches the true relationship, the true oracle, up to the value of chosen parameters. So you know that there's some parameters that perfectly fit the model, right? You have to have this assumption somewhere when you're talking about the convergence theorem, because otherwise you may just choose like the worst model possible. You may just choose like a constant function or something. And yeah, you'll still get some sort of loss out of that, but it won't be very useful. So what I mean by this is you have some true relationship. This is the model that you choose. This is like a perfect model that you've chose to try and fit it. And then obviously you tune the parameters and you end up with different values of your loss. And this is perfect. So what we're essentially doing here is we're just optimizing a function. We're choosing the three parameters, and then we're optimizing a loss, which is exactly what we did. I don't want to scroll all the way back, actually. It's exactly what we did in the previous theorem where we had a measurement function. That's exactly what we're trying to optimize. And so in this way, convergent regression is just convergent global optimization. And we immediately get this theorem out of it. So the parametric type here is searchable. That's the key part of it. And then we have the loss function, and any precision level, and any uniformly continuous model function. So what's weird here is what's Z? Well, Z is X to Y, yeah? Because as I said, it's general. We don't even require the thing we're trying to approximate to be a function if we don't want it to be. It could be like just trying to learn a value, like a simultaneous equation. but it works on functions. It's intended to work on functions, but it's general. We can use it on any sort of type. So we say for any searchable parametric type of parameters, any loss function on this oracle type, any precision level, any model, and some unknown oracle that we're trying to find, we're trying to compute, then we can always find some ideal parameter. This is not dependent actually on the type being searchable, although we do use its searcher a little bit. So we do require it to be searchable. There might be a minimum condition actually here, such that the loss between the thing we're trying to estimate and the model with the P0 set of parameters is at least as good as any other. It's the best possible one, basically. You know, it's the optimum choice of parameters, the argmin, or whatever you want to call it, for this particular function, for the loss function. And this is an instant corollary of the previous sort of thing that we weren't too happy with. So we're a bit happy with this, because what we're basically saying here now is, if we have some true oracle and we have some model, then we know that there's always some ideal set of parameters that we can get for any degree of precision. So we can increase the degree of precision, and we get different sets of, and again, these might ping pong around. We don't have the convergence property of like, oh, we're not going to deteriorate the output if we modulate the precision. But what we do get is we always get some answer that's better than all the others for any degree of precision. And I'm going, if I could briefly show you what that looks like in Agda, then we have the original minimization theorem here, where we say that there's some maximum argument for all these conditions for any measurement function that's continuous. We have this proof here, and then the proof that I just showed you that this function with a loss, the loss, sorry, here is by phi, not by L, so that might be a bit confusing. That's my bad. So if we have the loss function, we have the omega, then we can also minimize this function. And that's great that we can do that, but that doesn't tell us anything really about, so we know we can construct, this is like, again, a sanity check. We can construct an ideal parameter, but can we construct, you know, a good parameter, essentially? We know we can always construct the best, but this searcher could take forever. So how can we make this a bit more like actual parametric regression? And what we can do here is we take the same contingencies, but now our oracle, we know that it fits the model. So we have knowledge that it is a good choice of model. And if we have that knowledge, then not only can we just find the best set of parameters over the bunch that will fit any of, that will be better than any other set of parameters, but we can actually find a set of parameters that will be better than any degree of precision. Because essentially the proof here relies on the fact that the searcher, we use this as a predicate, essentially. We prove that it's a continuous predicate. We plug it into the searcher. We have a proof that it's satisfied by something because it's satisfied by P. And then we get this as an answer. We get this from the search condition. So it's 10 o'clock, so I don't have quite any time to run through how this works. But essentially, our regressor, if you want to call it, the thing that computes the arguments, is built from a searcher on those types and a lot of proofs of continuity. And what that means is that we can always compute an argument for the model, as long as our model is well chosen, which we have to have as a sanity check anyway. I've said sanity check too many times. That will minimize the loss to any degree of precision. And this goes right back to the start of the talk when we said this is what convergence is. So this is a convergence theorem. Apart from the fact that it will ping pong around, that can happen. That is like something that doesn't really relate to traditional kind of AI systems and all that. But this is a convergence theorem for regression on a general class of types that include types for exact real numbers. And we have a couple more theorems that are in the paper, which introduce error into the view of the oracle. So we don't just know the oracle, we get an error-prone version of the oracle that's more accurate to like data observations. We also have another proof that's not even in these slides, which is to do with kind of matching interpolation and regression. That's in the paper. So just briefly, the next steps for our research are, well, this is like a first step, this Agda formalization, in work connecting regression analysis, global optimization, and constructive real numbers. Our next step is to apply this framework to more practically available types, because we can compute all these algorithms for regression, but they're really inefficient because we're using them on these infinite sequence types, and we're pushing around so many proofs of continuity that actually it's very inefficient in the extreme. And so what we want to do is, well, we've got this formal framework. Can we apply it to like more practically available types for exact real numbers? For example, this CR Java library, which was developed by Hans J. Boehm 20 years ago, but is now the basis of the Google calculator. So if we can look at that and apply it in a similar way, can we get like efficient results that are also correct? So what I said at the start, local optimization is really efficient, but we have some issues with sometimes its correctness, whereas it's the opposite for global. Can we match these two in some way? That would be really interesting within our framework as well. And we've done some early experiments with this. It looks like a good direction. And as I said, we have to keep correctness in mind. We've got to do this sort of parallel development of algorithms and proofs, which is exactly what we've been doing all along. And just to kind of give an overall, probably won't have convinced you guys on this, but it's kind of our like underdog central thesis that formalized constructive type theory is actually an interesting perspective and an appropriate framing for work looking at foundations of machine learning, because what you can build is a general perspective and you can get verified algorithms from all your proofs in a really nice way that you can't always get in other settings. So I'll leave the slide with some links on, and I will end my talk there. So thanks very much for inviting me.